Welcome back to this NPTEL online certification course on molecular rearrangement and reactive intermediates. In the today's class, I am going to talk about carbene. So, I am going to talk about the generation of carbene and their bonding and some of the reaction and rearrangements. So, let us go to the first slide of the today's topic. I am going to talk about the definition of carbene and then their structures. I am going to talk about the singlet and triplet carbene and what is the difference in the reactivity, try to explain some of the facts through the molecular orbital diagram, and the lectures will end with several different generation method of carbene. So, first thing is why we want to study carbene. I think once you try to study some topic, we should ask ourselves why. The question is, by studying carbene you can able to learn how to convert this olefin to this corresponding cyclopropane. You can learn that how to convert this 1,2-dicarbonyl compounds to this corresponding ketene, and then from the ketene you can synthesize variety of compounds. So, that is a reactive intermediates again. Then from alkene to alene, so that is the alene structure. Then homologation of carboxylic acid, starting from this carboxylic acid you can able to introduce this CH2 group here. Then there is some reaction called CH insertion. So, you can see from this diazo compound you can form this some sort of a fused 5-member ring. Okay. So, these are the different type of reaction you can only able to do if you can learn about carbene and their reactivity. So, if you try to define carbene, it is a divalent species, okay, and having so the most important thing, having electron sextet. That means there is 6 outer electron, that means it will try to, so that means it is a electron deficient species. Okay, so, it will be reactive, and because it wants to go to the octet. Okay, so, highly reactive, and then it is short lived. That means if it is it forms, it will react fast till it is forms a stable compound. And then of course, there are 2 covalent bonds as I mentioned at the beginning. So, now I said the carbenes are short lived, and so that means is that true for all the carbene? There are scientists who try to isolate them. So, the first effort was by Walczyk. So, in 1960, when they try to isolate the carbene from the pyrolysis of this compound which can release the chloroform, what end up, instead of isolating this compound, it actually forms a dimer. So, later Ardungo group actually realized that how to stop the dimerization. So, what they have done in this imidazolium chlorides, they introduce this adamantyl group. So, once you introduce this adamantyl group here, now it will be very difficult to form a dimer. So, using sodium hydride they can able to abstract this proton which can able to end up generating a carbene species. So, this carbene is well characterized, you can able to get the X-ray crystal of this, from there we can able to calculate the bond angles and all other fact. So, it turned out that this is a carbene of this is a singlet carbene. So, now we are going to try to classify the carbene into a singlet and triplet. Okay. So, before going to the classification, so let us try to go through some of the discovery. Of course, so this is a discovery timeline, and I cannot read every single thing. I am just going to highlight some of the important discovery. So, this is for you for your understanding about how this chemistry actually developed. So, first thing in 1855 Guether and Hermine, they actually able to report first to propose the carbenoid intermediate. So, they are the first to propose that using chloroform and the sodium hydroxide, they can able to propose that formation of the CCl2. Later the Neff able to introduce this particular transformation using that particular carbene which can give you this 3-chloropyridine. Then the Gomberg in 1900 actually discovered that. So, this is the first example of a free radicals. Later on actually there was several different discovery about the diazomethane for the ring expansion of benzene to the tropolone. It is a one of the important discovery. Then Simon Smith Smith reaction for converting this double bond to cyclopropane. Then another important discovery formation of this metal carbene complex is great Fischer carbene, and then the Schrock which actually found the D0 metal alkylating complex called Schrock carbene. Of course, there are numerous research, and then as I mentioned that Ardungo group actually first found out the first able to isolate a stable isolable carbene. After that, in the last 3 decades, there are a lot of discovery in this area and lot of new reactivity was discovered. So there are the nomenclature of the carbene we can talk about. So if you just a CH2 carbene, we call it methylene. If it is from a phenyl and a hydrogen here attached with the carbene, we call it phenyl carbene. If it is a dichloro here, we call it dichlorocarbene. Then the bromochloro difluoro. But if it is coming from a cyclic cyclic ring like a 3 member or 5 member, we call it cyclopropylidene or cyclopentylidene, very similar to vinyl. If you have a vinyl group with a carbene, we call it vinylidene. Okay. So that is some sort of a difference in the nomenclature. So now I came back that the topic I was trying to discuss, that the difference between singlet and triplet. That means carbene, once we write something like this, we are not specifying anything here. We are just saying this is a carbene. But now we have to kind of from there we have to come back and try to discuss that there are 2 different types. One is called singlet carbene and one is called triplet carbene. In the next couple of slides, we are going to learn what will be the structure, what will be the bonding, what will be the hybridization, what will be the bond angle between this RCR. We are going to learn everything. Okay. So in general, what we are seeing here, generally in this carbene having a sp2 hybridization for this carbon. Okay. And now you can see there is a vacant p orbital here. Okay. And now these 2 electron which of these actually are pair off into this sp2 hybrid orbital. And here you can see number of unpaired electron is 0. So the total spin actually 2s plus 1 going to give you 1, which is, that's why we call it singlet. Once you come to in case of triplet, what is happening now, instead of the pairing, now each electron is one is in the sp2 hybrid orbital and the other one is in the p orbital. Okay. So now you have 2 unpaired electron here. So number of unpaired electron is 2, and if you take the total the spin, it will be half plus half will be 1. So 2 into 1 plus 1 is going to give you 3. It is called triplet. Okay. So now in general, if you see the carbenes like CH2 or CHPH, CHR, CPH2, these are the carbenes mostly are triplet carbenes. Okay. But if you see something like a like a group which can have a non-bonding electron, like have a lone pairs, like CCl2, CHCl or COMe2, you can see, or here with you have a nitrogen next to this carbene. So in these cases you can see these are forming singlet carbene. So we can understand some of the presence of this group versus you have a chlorine versus you have a CHPH. So now we try to even understand what is why if you have a 2 chlorine or why if you have a just a phenyl ring, why they are becoming a singlet versus a triplets. Okay. So now we are actually trying to understand them very details, that we first have learned that they have a sp2 hybridization. Now the important concept is about the bond angle. So you can see that in case of triplet, the bond angle between RCR. So we are talking about this particular bond angle here. So now you can see this bond angle we are talking about is 130 to 150. So now the question comes, why in case of the singlet the bond angle is 100 to 110, in case of triplet is 130 to 150. So what is happening in case of singlet? In case of singlet, you can see the bond, because you have 2 electron paired up in this orbital and this is sp2 orbital, hybrid orbital. So now there is a repulsion between these bonding pairs and this 2 electron pair which is in this hybrid orbitals. Due to this repulsion between this R group and this orbital, now what is happening, that is why the bond angle is less compared to a triplet, because in triplet now you have only single electron here. So the repulsion will be less compared to comparatively with the singlet. So that is why you can see the bond angle will be higher. We have already clearly learned that they have we have seen in the previously that they in case of singlet there is no unpaired electron. So 0 unpaired electron, that means these compounds will be diamagnetic. Now here it is paramagnetic because you have 2 unpaired electron. We know about that. Make a compound paramagnetic, it has to have a unpaired electron. Now the energy of so always you can see the singlet will be higher in energy compared to triplet. triplet will be a more stable state compared to a singlet state. Okay. And as you can see, these compounds are diamagnetic, so you cannot see a peak in the ESR spectrum. Okay. But because these are these triplets is paramagnetic, you can able to see the ESR spectrum. So you can able to find out the generation of triplet carbene through the ESR spectroscope. Then there are reactivity. We are talking about their reactivity. So in case of singlet carbene, as you can see, singlet carbene has a vacant p orbital, that means it can able to accept electron density here. That means if you have a nucleophile, it can give electron density to this, and it has 2 electron in the sp2 hybrid orbital, that means it can also give this 2 electron to electrophile. So this means this can be both electrophilic and nucleophilic. But here in case of triplet, it is mostly acting as a diradical. Okay. So now I am going to show you some of this molecular orbital diagram about these singlet and triplets. So again we are trying to show you that that here you have this sp2 orbital in case of triplet, which actually did not participated in the so it is actually stays here in the same orbital as a pair, and now it is actually you have this 1s orbital of this hydrogen. If you talking about CH2, then we are talking about the 1s orbital of the hydrogen, which is actually forming 2 sigma bond. So this sigma bond means I am talking about this sp2 hybridized bonds, and there will be a sigma star, okay, which is unfilled. And then you have very similarly, if you come for the triplet carbene, the only difference you can see, now you have 1 electron in the p orbital, which is empty. Okay. In case of singlet it was empty, but in case of triplet you have a single electron there. So you have 1 electron in the sp2 and 1 in the p orbital. So now I am going to talk about the factors that determine the multiplicity. That means we have learned that if you have a CCl2, we are talking about a singlet. If you have a CHPH, I am talking about triplet. But is that all, or there is something else we can learn where we can able to use these values or understand that why something is triplet and why some of the carbenes are singlet. Okay. So here we are going to learn about 2 important things. One is the Coulombic repulsion or EC, and the other is the sp to 2p energy difference. So in case of the singlet carbene, because the 2 of the electrons are pair up in this 1 orbital, they can have a repulsion. So this is called a Coulombic repulsion, and that is how this energy, so EC comes to the account. And the other one is that the gap between this sigma and p, that means this is the sigma, means this is this hybrid orbital, and this is the so this is the p orbital which was empty, but then in case of singlet you have a 1 electron there. So now the gap between this sigma and p orbital is the another factor for triplet carbene. Now I am trying to explain you why that gap is important, because this singlet triplet splitting, that is delta GST actually is depend on the EC and minus of delta E. So what we are finding that depending on the delta E value, if your delta E values become higher and higher, so if your delta E become higher and higher, what is going to happen? If it is higher, then slowly the delta GST will be negative, okay. So this value will be negative. So that means once you go from positive values of delta GST towards the negative values, what you are going to observe, you are going to slowly observe that this is happening because this delta E, that means the gap of sigma and p is getting increased. As that is going to get increased, it will slowly convert to a singlet carbene. So that means you can see here, so in case of CH2 the value is 9 kilocalorie. Okay. Now you can see that I am going to show you some some more example there, where you can see that the values can go to even to a minus values. Okay. So now I am going to tell you that based on the different type of groups around this carbene, means those 2 substitution, what can be, we can classify them into 3 different type of interaction. One is X type interactions, Z type interactions, and then C type interactions. So so what is happening here? We are talking about in the X type interactions those carbene like CCl2 dot, double dot, so this type of carbene, or CF2. So we are talking about this type of carbene here. That means you have a pi electron donor which can raise the p orbital like Nr2, OR, fluorine, chlorine. So this type of group, if it is present, what is going to happen? This can raise the p orbital. That means because you have a non-bonding electrons which can be given. So now this can raise the p orbital. So that's how what is going to happen. Now you can see the gap between this. So now if you have to be triplet, then there is one electron from here to migrate to here to here. Now that is getting very difficult because this gap is getting very increased. So if this gap is increased, that means it cannot possible. So that means it is going to stay as a singlet carbene instead of the triplet. Then the other interaction called Z type interaction. We are talking about pi electron acceptors. So previously pi electron donor, now pi electron acceptors. And that means if you have a carbonyls, SO2 air, nitro, those type of groups are there. That can take the electron density. If you are taking the electron density, what is going to happen? End up now your P is getting more stabilized. Instead of the destabilization, your P getting more stabilization. So now what is going to happen? Now the gap will be sigma P gap will be less. So now it can able to easily go to the corresponding triplet. So that means in this scenario we will mostly see a formation of triplet carbene. Now there is other type. If you have a group where conjugated group. So if you have a conjugated group, then like alkynes and aryls, then depending on the different substitution on this alkene, alkyne and aryl, it can either remain like a neutral, like unaffect, or it can lower. That means if it can lower, what is going to happen? That means if it is going to lower, then it's very similar things happen, that it can give, if the gap between this sigma and P going to get decreased. So that means there is a formation of the triplet carbene. Okay. So here are some of the values. Here you can see this is a triplet carbene which is having 9 kilocalorie per mole. Now you can see here, once we introducing those groups which can have a lone pair or the non-bonding electrons, you are slowly going from triplet to singlet. Okay. Again I am trying to explain this, that if you have a hyperconjugation effect, okay, what is the hyperconjugation playing role? Again hyperconjugation means giving electron density, the CH electron density to the empty orbital. Now if you have a, like, as you are increasing the hyperconjugation, means you are going from this direction, that means the hyperconjugation increases. That means 1 you have a methyl, 3 hyperconjugation versus 6 hyperconjugation. You can see your value become 2.26 to minus 2.47. That means slowly it is going to singlet carbene. From triplet it is going to singlet carbene. And now if you come to something like this type of scenario. So here what is happening, if you have this group like 2 orbital group, then you can see the value is 2.65 kilocalorie. Okay. So that means in this case what we are seeing, this carbene as a triplet. So that means if you can think about the inductive effect, then you might think, sir, we have an inductive effect from the orbital group, that means it is giving electron density. So why it is triplet? Because there is another effect called steric effect. So that is also important. I told you at the beginning that in case of singlet there will be a interaction. I think I mentioned before that once you have this pair here, and then once you have this 2R group here, I told you there is a interaction between this the bond pair and this pair, which is in the sp2 hybrid orbital. Because of that, this angle was, remember I was telling you, this angle is 110 degree, correct, approximately. So now once you have a bulky group here, because the steric will be even more once you put a orbital group here. So that's why because then it cannot able to achieve the geometry for a singlet. That's why it is going to stay as a triplet. In case of triplet, because of the less repulsion, the angle can be up to 130 to 140 degree. So I have already talked about their geometry, their molecular orbitals, and now I am going to talk about some of the method how to generate carbenes. Okay, so there are different methods like fragmentation reaction, I am talking about elimination reaction, and then you are going to find from organomercuric compound how to generate carbenes. So let us start about the diazo compound. I think this is a very important compound. At the same time, this is this compound is very explosive. So if you are working in the laboratory, you should be very careful using what type of glassware you should choose. Okay, so there is a particular glassware which is used for these particular compounds. So this was discovered in 1894. Okay. So we always, I think this compound, the compound called diazomethanes, which always I think the structure is CH2N2. So, here I am talking about that this compound is always, you can make a ethereal solution of it, and now once you take this diazomethane and go for a photolysis or thermolysis or using metal catalyst. So, from this compound it will go to forming this carbene, okay, via photolysis, thermolysis or metal catalyst. Okay. You can see here that I think we can able to draw the the resonance structure of this compound. So, if you have CH2 in place of R, then that is the diazomethanes, it can form this N2 plus and then minus, and then finally it can able to cleave this bond under photolysis or thermolysis to generate this corresponding carbene. So, as I said that the synthesis of diazomethanes are a little bit tricky. Okay. So, that means so that is why there are several groups found a different approach, that means you can make diazomethane, but from a precursor compounds. So, one of them example is N nitroso derivative of urea. Using the N nitroso derivative of urea, using this compound, in place of KOH, it can form it can form this particular intermediate. So, let us try to understand what is the what is the mechanism here. The OH minus actually attacking here, and then you can see, so it will forming the N minus, then it is going to come back and get rid of this part, which can take a proton to form this intermediate. Now, once this one getting treated in place of a base, is going to take this, it is going to abstract this proton and then form this N minus, which is going to finally this lone pair of nitrogen can form this N double bond N to finally form the diazomethane. From N nitroso derivative of sulfonamides, very similar thing happening here, in place of KOH, it is cleaving this bond, forming this intermediate and finally forming diazomethanes. N nitroso derivative of amide, again very similar thing, base going to attack here, this part going to come out and then form diazomethanes. From hydrazones also, using mercury oxide also diazomethane can be, not a diazomethane, but it is a diphenyl diazomethanes can be synthesized. So, now I am going to talk about some interesting reactivity of diazomethane. So, diazomethanes are very much important compound, as I said, it is known for this particular transformation. So, if you want to transform this carboxylic acid to ester, then diazomethane can be used. So, here what is happening, the diazomethane has a CH2 minus, it can abstract this acidic proton, then to form this corresponding O minus species. So, this is can this O minus can attack here through the CH3, release of N2 can form this compound. Okay. So, now the question comes, does the reaction happens if you have instead of acid you have simple alcohol. Okay. So, if you have just a N-propanol, then there is no reaction is happening, but if you have a phenol, that the reaction still works. Okay. That is because this depending on the pK. Okay. So, depending on the pK, if the proton is little bit of acidic, then only this reaction happens. But if you want to make this transformation, so if you want to make this transformation working, what will be the product? Let me just write down the product. Then you can able to achieve it, but not just by using diazomethane. You have to use H nu or some sort of a UV radiation. If you do that, then you can able to convert this corresponding isopropanol to this OME product, means corresponding ether. Okay. So, here what is happening, in place of light or in place of the photolysis, this can form the corresponding carbene. Now, carbene is going for a CH insertion. I am going to discuss all these different type of reactions. So, here the carbene is going for a CH insertion, where this oxygen lone pair now can attach to the vacant orbital of this carbene, followed by it can capture this proton get captured by the CH2 minus to form this corresponding product. Again there are generation of carbene. So, here I am going to talk about the generation of carbene from diazomethane. If you use this H nu under the direct excitation, then it can generate a singlet carbene, but if you use a photosensitizer, then what is happening, in place of photosensitizer it can convert to corresponding triplet carbene. So, you can use several different photosensitizers are known, I think benzophenone was used for this purpose. So, now I am going to move forward and talk about the Bamford-Stevens reaction. I think all of you are very familiar with these reactions. Okay. So, in the Bamford-Stevens reaction there is actually two different protocol. In one case it can goes from a formation of a carbocation. If you use a protic solvent, if you use a aprotic solvent, then after formation of this hydrazone, what is happening in place of base, it is actually forming a carbene, and from the carbene what is going to happen, it is going to go for this the CH. So, this CH go for CH insertion, which can end up forming this corresponding olefin. Okay. So, we have shown here the mechanism. So, in place of base, it is going to abstract this NH proton to form the N minus, then release of SO2 air group, then generation of this intermediate, and then after that the release of N2 in place of aprotic solvent actually generate this carbene pieces. Okay. And if you have a protic solvent, then from here instead of carbene it will generate a carbocation, and after that there will be proton abstraction to go goes to very similar product. So, now I am going to talk about another method of generation of carbene from ketene. So, using ketene also, if you can go for this the pyrolysis or in place of H nu, it can able to convert to this corresponding carbene, but again it was reported that in case of ketene can also goes for polymerization in under those conditions. Okay. So, here are some other example of generation of carbene from strained molecule. So, you can see from this strained cyclopropane, it can actually goes for some sort of a, you can able to draw maybe this type of arrow to show them that that is happening. So, it is cleaving here and this bond can move this direction. So, that means this part is getting out, forming this corresponding dichlorocarbene. It can happen here very similarly this part can chop under photolysis to form this CH2 carbene or methylene. So, if you can confirm them by doing several transformation, one of the important transformation is if you can add to a olefin. So, you can from the stereo specificity you can also find if it is a singlet or a triplet. Okay. Then from phenyl oxyrene under pyrolysis it can also cleave here to form this corresponding carbene and then the benzaldehyde. And then again from this compound also it can get to the corresponding aromatic compound and it can able to form the corresponding carbene as well. So, there are other methods for the formation of the diazirines. So, diazirines is another important compound or an important precursor which can also generate the carbene. Here you can able to synthesize from corresponding carbonyl to diaziridine, which can further oxidize to corresponding diazirines and which can under photolysis or thermolysis can generate carbenes. Here are some of the example. Depending on the different groups here, that means if you have phenyl and CF3, it can generate a triplet carbene under photolysis. Again here we are showing that if you have a nitro group here also it is generating a triplet, but if you do not have CF3 group here, then under photolysis actually it is generating a singlet carbene. So, here are another method of generation of carbene through the, as I mentioned, that you are actually cleaving of the sodium trichloroacetate. That means once this bond goes for a decarboxylation, because this is going for a decarboxylation because you can see that the CCl3 minus is now going for alpha elimination. Okay. So, first is going for a decarboxylation, then alpha elimination to generate this corresponding dichlorocarbene, or from organomercury compound under heat it can also generate this type of dichlorocarbene or this the chloro CF3 carbene as well. So, here is the example of alpha elimination. I think alpha elimination is a very important reaction and it was I think it was discovered the early, it was the one of the early discovery of carbene, where using NaOH and chloroform it can form this the dichlorocarbene, which is still useful in the organic synthesis. Here is one of the important fact about it, that if you have a trichloro species like this, then using potassium terbutoxide you can able to abstract this proton to form this CCl3 minus, then alpha elimination from here to generate this carbene. So, what we are talking that from if you have a trichloromethane versus if you have a dichloro, what is happening, the pK of now this hydrogen is going to get changed. That means, now what you have to do, you have to use stronger and stronger base. Once you have the monochloro versus dichloro versus trichloro, the proton become more acidic. That means, you can use a milder base if you come here, but if you can come to this where you have a 1 chloro, then you have to use something more stronger base, because the pK is, so this is literally alkane which have a pK around 50. So, you have to use a stronger base to generate this corresponding anion, which can go for alpha elimination to generate the corresponding carbene. So, here I think the final example here, that if you have a strain alkene, because if you have a strain alkene, because of the steric things, and so there is a this pi bond become weakened because of the steric region of these two different groups, this pi bond become weakened. Okay, because the pp overlap, because the overlap of this p orbital got disturbed because of the planarity issue. As a result, what happened, so because the energy got raised, so after hitting this particular compound, it forms this corresponding carbenes. In this part, I actually teach you the definition of carbene, different variety of carbenes, and the singlet triplet carbene and their generation. In the next class, I am going to talk about different reaction and the rearrangement. Thank you for coming to the class, and thank you, and I am going to see you in the next class.